Now let's discuss the last two parts of centrifugal pump. So in these last two parts, we will talk about cavitations and net positive suction head. So these two sections are closely related. And now let's begin with the cavitation itself. So when vapor bubbles formations of the liquid appears on the impeller or in the blade, due to the local absolute static pressure of a liquid falls below the vapor pressure. So this phenomenon of cavitations is mainly occurs at the suction side or at the eye of the impeller. Visually, we can observe the cavitations by seeing bubbles surround the impeller or the eye of the impeller of a centrifugal pump. So when these cavitations occurs, we can hear a higher noise and it increase the vibrations of the pump and it might cause a crack on the structure of the impeller. Moreover, it will lead to a decrease in the pump efficiency. In order to describe the cavitation itself, we can use the cavitation parameter. In this term is also called as tau. So we have several terms use this tau or this Greek letter to represent it, but do not get confused. We are now talking about cavitations and tau is the cavitation parameter. So cavitation parameter itself is a ratio between the pump total inlet head above vapor pressure divided by the head developed by pump or H. So the pump total inlet head above the vapor pressure can be called as the net positive suction head, and it is a function of where Pi is the pressure of the pump or pressure of the fluid above the vapor pressure divided by density multiplied with gravity plus velocity to the power of 2 divided by 2 times gravity minus to the vapor pressure divided by density multiplied with the gravity accelerations. So it can also be described as the available energy at the suction side or at the eye of the impeller. To describe the cavitation phenomenon and the NPSH, let's have a look. Let's assume now we have a reservoir or a bucket of water or a tank of water with the fluid level of A. Here we have A as fluid level. And then it will be the inlet of the pump or I. We have I as the inlet of the pump and A is the water level at the tank. Now assume that the energy at point A is equal to the sum of energy at the inlet of the pump plus the energy loss between the water level to I. So we have losses due to pipeline, fittings, valve, and so on. And yeah, it's here the sum of losses. We know that the energy at point A is equal to pressure at point A divided by density, gravity accelerations, and the velocity of fluid at point A divided by 2 times gravity plus ZA minus to this parameter at the pump inlet or at the when it reached the suctions of the pump. And in most cases at point A, the velocity and the elevations is or are equal to 0. Therefore, we can write down the equations as pressure at point A divided by density and gravity equal to pressure at the inlet of the pump divided by density and gravity plus the velocity at the inlet to the power of 2 divided by 2 times gravity plus the elevations at point or at the inlet plus the losses at the inlet and the losses due frictions at the inlet. Or these three, we can combine them as the head of the suction side. And as we know, the cavitation parameter or tau is equal to the pressure at point A divided by the density multiplied with gravity minus head at the suctions minus to the vapor pressure divided by the density multiplied with gravity and head available at the inlet of the pump. And in order for us to avoid the cavitations, we need to have the value of tau or the cavitation parameter to be higher than the critical cavitation parameter value. So this tau c or cavitation parameter, critical cavitation parameter value normally comes from the manufacturer of the pump. So it will be given to the user of the pump. Then we have to avoid this number and has cavitation parameter higher than the critical value. Another parameter that we need to look at to avoid cavitations during the operational of a pump is the specific speed at the suctions of the pump, and it can be estimated as the specific speed multiply with the flow rate to the power of 0.5 divided by gravity multiply with the net positive suction head to the power of 3/4. The suction specific speed can also called as a functions due to cavitations that influence the pump efficiency, and this parameter is a dimensionless or non-dimensional specific speed at the suction. So we can use this number to as one of the way to estimate the cavitation parameter, or it can also be written as specific speed divided by the specific speed at the suctions, that is equal to the net positive suction head to the power of 3/4 divided by the available head at the inlet to the power of 3/4, or is equal to tau to the power of 3/4.